All right. Today we're doing one of my favorite things. This is the day we're learning the molecular shapes using the VSEPR theory. VSEPR stands for valence shell electron pair repulsion. And so what that really means is when you have lone pairs on the central atom, it repels bonded pairs, and that's what gives these molecules shape. So in order to do VSEPR, you first have to understand what is meant by areas of electron density, because that's what's going to determine the electronic family or the electronic structure leading to the actual shape of something in space. So I'm just going to draw a couple of molecules, and we're going to determine areas of density. What is an area of density? A lone pair, a single bond, a double bond, or a triple bond. All of those are one area. So how many areas of electron density you go when you have your Lewis structure, which you need. You can't determine shape just by looking at a formula. You have to draw the Lewis structure. And once you have the Lewis structure, you look around the central atom and you determine areas of electron density to then figure out what family we're dealing with. So how many areas is this? 4. Okay? And if I have something like what you built just now is CO2, how many areas of electron density is this? 2, right? What about, I'm not going to put the electrons on the outside just for time's sake. How many areas? 3. All right, do you kind of get it? So if I had water, how many areas? 4. Okay, so that's what we're referring to when on the chart that you're looking at here, the table says areas of electron density. That dictates what family you're in or what the electronic structure is. So regardless if they're lone pairs or bonds, the number of areas tell you the family. So we're going to start, you guys are going to fill this table in. We're going to leave hybridization for a later day, and we're going to go all the way through molecular polarity. I'm going to take one pass through to bond angles, and then, I know I told you something different a minute ago. Stop me at bond angle, and then we're going to go back through and do polarity of all of them together. So because I'm on video, I need to do it with these so people can see at home what I'm talking about. You guys are going to be building these. All right, so we're going to start with our 2 areas of electron density. 2 areas, so everyone has built CO2. You're supposed to build it on, are you missing? Is that all the pieces you have?
That's all the pieces I got.
This is why I get really frustrated and I can't let people use kits because things like this happen. Put everything back in here and then put it on my desk. Okay, if you have 2 areas and all of them are bound, both areas are bonded, we call it, it's electronically linear. So the family is linear, and then the actual molecular structure, when all the areas are bonds, it's the same name. So this is linear, linear, electronically and geometrically. Now looking at that molecule, what would the bond angle be? 180, right. From here to here is what we're looking at. 180 degrees. And that's a pretty easy one. So are we good with that? Okay. So now what I want you to do is we're going to move on to 3 areas. You're going to break one of those double bonds, take one of those double bonds off entirely, leave one on, and then put 2 fat skinny bonds on there and attach whatever color, it doesn't matter, to make 3 areas. So, all right, so this is your 3 area thing right here. This is all of these, both of these scenarios on these pictures are 3 areas. take a look at your 3 area. What is its geometric shape if you just look at it straight up? It's a triangle, right? But notice it's flat. You can put your hands on it like that. It's flat. Because it's flat, we call it trigonal planar. Okay? So that's the family for 2 different structures. If all the areas are bonded areas, the molecular geometry is also trigonal planar. Now, taking a look at your little model there, what are the bond angles that exist between these? Yeah, it's 120, right? It's a triangle. So this is 120 degrees. All right? Okay, looking at this. This is 3 areas. We have a lone pair up here. Still in the trigonal planar family. So what I want you to do with your model is take one of those single bonds off. This lone pair, this is where the whole concept of valence shell repulsion comes in. This lone pair repels these bonded pairs. Okay, so that makes this shape called bent. It's still trigonal planar electronically because there's still 3 areas, but its actual shape in space is bent. Put it away. Okay. All right. What would the bond angle be? Let's talk about it. This lone pair is repelling the bond angle in. So it's going to be less than 120. And that can be your official answer, but if you're curious, it's about 117. I'm not going to hold you responsible. That's not a piece you have to memorize. You do need to know the 120. But all you need to know is as you progressively add lone pairs, bond angles get more and more compressed. So that's our area of 3. How are we feeling about 3? Can we move on to 4? All right. All of you have a black carbon that's got four holes. Fill those with 4 squatty bonds and attach 4 things to it. You should have enough whites to just put 4 whites, little hydrogens on those carbons. And that would be methane. Did you say methane? All right, so this little methane, the CH4, has got 4 areas. And what is the family for all of these called? Tetrahedral. So these are electronically tetrahedral. Okay. Oh, that was a Labrador. All right. If all 4 of the areas are bonded areas, the name geometrically is tetrahedral. 4 bonds, no lone pairs. Now this is a special bond angle that you do have to memorize. Can anybody remember what it is? 109.5. So rather than memorizing 4 and 0 is tetrahedral, 3 and 1 is blah, 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 I think through it. I think to myself, okay, this tetrahedral, I know it looks like a Martian with 3 feet and no arms. I see it like a little robot. Okay? If we take one of the bonds away to create a lone pair, I think of it as this guy losing his head. And this is in my head visually. I'm doing that. So what's left is this little tripod-y looking thing, right? It's just the Martian's feet. This lone pair up here that's been created is repelling those other bonds. So this is a pyramid that has a triangle base. So we call it Trigonal Pyramidal. Trigonal Pyramidal. So what did this lone pair do to our bond angles? it decreased it. So your official answer could be less than 109.5, but if you're curious, it's about 107-ish degrees. So that is 4 areas, 3 bonds, 1 lone pair. All right, now if we have another lone pair, 4 areas, still tetrahedral electronically, but now we have 2 bonds and 2 lone pairs. What does that look like? Y'all recognize this shape. Bent. What's the most common substance that has this geometry? Water. Think about water. It's got 2 hydrogen bonds and 2 lone pairs on the oxygen. That's what this is. Okay? So our 2 lone pairs that are here cause additional compression of this bond angle, repelling those bonded electrons. So this would be, we have a tradition at Westlake just saying less than 109.5, less than this. If you're curious, it's about 104-ish. And the reason I say ish is so many different textbooks have different values, and they're not important enough to memorize. Okay? What's important is that you know the angles get smaller. So we good with 4. Okay, let's move on to 5. For number 5, there's different colors. There's dark navy, which almost looks black. There's a longhorn orange, and then there's a tan. So find the one you have that has 5 holes. And there's apparently a, no, that's 6. It's your tan one. That's 6. That's correct. So build your 5, family of 5. Okay, so a family of 5, if you have 5 bonds and no lone pairs, or just 5 areas in general, if you look at this structure that you're building, do you notice it's like a pyramid on top of another pyramid? And those pyramids have a triangular base. That's what makes it trigonal bi-pyramidal. Or bipyramidal, as some people say. Trigonal bi-pyramidal. Okay, so I want you to look at this structure and realize that there is an axis to this. Okay, if you look, there's an axis going up and down, but there's also an equator. So I need you to hold it and recognize that. Do y'all see that? Okay. Why that's important is there's 2 types of bond angles with this. So right now, I want you to look at the axis to the equator bond angle. What is that value? 90. So from here to here, we have a 90-degree bond angle. Okay? Now, take the little thing you're holding and point it toward your face so you can look equator to equator. What is the equator to equator bond angle? 120. So there's 2 bond angles in this, and that's why you have that little slash in your box there. That's 120. All right. So if you have 5 areas, those bond angles, I didn't say the electronic structure is trigonal bipyramidal. The geometric structure then is also trigonal bipyramidal. Now, this is going to be hard for people to video to see, but I need to show you this. You can't just take off anything for your next lone pair. When lone pairs are formed, there needs to be an alleviation of what we call bond strain. Just watch. If I were to take off this top guy here, one of the axes, do you see how all my bond angles are still 90? I've really done nothing electronically or energetically favorable by doing that. However, if I take off the equator, what do you see that's happened? We created a 180, didn't we? That alleviated some bond strain. So when we lose electron, or when we have electron pairs in a trigonal bipyramidal situation, they're on the equator. So go to town, put it on your desk, have at it. because I'm not going to ever let you do this again. This is called what? Seesaw. Have fun. Make a lot of noise. You've got about 10 more seconds to go to town on that. I'm wondering if they can hear this. I bet you. I think this might actually be a noise that makes it onto the video. All right. And Finn. All right, good. That was very, very nice. So our seesaw is still trigonal bipyramidal electronically, but it's got 4 bonds and 1 lone pair. Let's talk about the bond angles. This lone pair compresses. So what happens to both our bond angles? Less than 90, less than 120. I think it's like 85-ish and 117-ish, but again, doesn't matter. All right, now we're going to lose another from the equator. And we're going to be trigonal bipyramidal, but this time we have 2 lone pairs and 3 bonds. 2 lone pairs and 3 bonds. I pitied a fool. Do y'all know who that was? Mr. T. I'm glad somebody knew it because I was feeling really stupid. Yeah, Mr. T. This is T-shaped. That is actually the name, T-shaped. Seesaw has another name. A regular tetrahedron is another name for it, but it's commonly now known as seesaw. Okay, now look. Do you see how our equator to equator bond angle disappeared? So we now are back down to only having 1 angle, and it was that 90. That's now even more compressed. So our bond angle here is going to be even less than it was before, less than 90. And again, that's a conceptual thing you need to know, not an actual value. All right, so take off your last equator. Poor little bonded electrons. I feel really sorry for the guys in these bonds. Because what's happening, we got these lone pairs repelling them up and down and all around, and they're like, ugh! So what happens to their bond angle? They go back to 180. And what would this be called electronically? Trigonal bipyramidal. Geometrically, it's linear. Okay? All right. Let's build up our last one. It's going to be lavender, silver, or is there a 6 tanner? Okay, a tan one. I thought all the tan ones were. I guess it doesn't matter. You guys can count the holes. All right, fill those up. If any of you played old school jacks, I made the mistake last period of asking if any of the girls played jacks, and one of the boys said, I did, and I was like, I'm so sorry. I need to learn. Gender's fluid. Have any of y'all played jacks in your lifetime? Yeah? This is what a jack looked like. Okay. It's where you had a whole bunch of little things and you throw them on the ground, and then you have a ball and you bounce the ball and pick up 1, and then you pick up 2 before the ball hits the ground, and you catch the ball, and you pick up 3 and catch the ball. 1Zs, 2Zs, 3Zs. It was a good game. Good times. Then there were Chinese jacks. Some of you know those. Same concept, but there's no ball. And the jack is just a plastic ring with a bunch of other little plastic rings attached to it. So it's like a mess of plastic rings. And you do the same thing, but you throw up one of the sets of rings and then grab, as opposed to bouncing a ball, but whatever. Look it up if you're interested. It's an interesting concept. But moving on. This is 6 areas. What would this family be called? Ooh, these are individually movable. Does anybody remember what this family is called? Octahedral, electronically. Why oct? There's only 6 things attached. Exactly. If you were to connect and make the faces, there are 8 faces. 1, 2, 3, 4, and you flip it over, 5, 6, 7, 8. That's where it comes from. Okay? So, this is 6 bonds, no lone pairs, also octahedral. The bond angles are easier in this one. It may come across to you when you're holding it, oh, there's another axis and an equator, but it's not. Because if you turn it the other way, oh, it's an axis. So there's no true axes for this. So all the bond angles are the same, and what is it? 90 degrees. Okay, because all the bond angles are the same, it doesn't matter where we have a lone pair. So when we take off one of those bonds, we have a lone pair. If you sit this on your table, you can see it's flat on the table, right? So it's a pyramid again, but what is this, the base's shape? Square. So this is called square pyramidal. 5 bonds, 1 lone pair. Still 6 areas, still octahedral electronically. And please, you've got to know the difference between the electronic versus the geometry versus the actual molecular shape in space. In Chem 1, people would get them confused. We can't have that happen in this year. Okay? Electronically refers to total number of areas. The shape then is dictated by number of bonds and number of lone pairs. Okay? All right. Bond angles here. We have a lone pair. It is repelling some of these. That lone pair on the bottom is repelling these bonded pairs because our lone pair is down here. So these are being repelled. What happens to our bond angle? Less than 90. All right. Now, there is a little bit of issue as to where the next electron pair needs to be if you have two pairs and 4 bonds. Lone pairs don't like each other. They want to be as far apart from each other as possible because they take up a lot of space as they're moving around. So where do you think we should remove the bond from? On the opposite side, right? So that creates now another flat substance. It's a plane, but what's its shape? So this is called square planar. Now it's kind of a similar situation as with the linear in the last set of family in the Trigonal Bi-Pyramidal. We have a lone pair on top repelling down. We have a lone pair on the bottom repelling up, and so everything's like to a halt. All the bond angles are back where? 90. Okay? All right, so now we're going to talk about polarity. And those of you at home, you can fast forward if you need to, because unfortunately you're not going to see this. But I'm going to need 2 volunteers that don't mind me pulling on them. Okay, you 2. First ones I saw. Up. All right. First thing I want you to do, and you can write it down in a minute. I want you all to write down the definition of what we mean by molecular polarity on the bottom of that chart. Molecular polarity is an uneven distribution of electrons. If you're ever asked, why is that molecule polar, you need to say there's an uneven distribution of electrons. You can't say the molecule's not symmetrical. You can't say there's different things attached. You have to say uneven distribution of electrons or uneven distribution of charge, something to that effect. So let's talk about this. JD, who's going to stand up, he's in the center, and he's going to be an atom that has 2 areas available for bonding. So stick your arms out to the side. So if you notice, he is at 180 right now, right? So Annalie and I are going to have equal electronegativity. So grab his wrist and literally just face forward and lean. Notice there's no net movement on this, right? If you drew vectors to describe this, they'd cancel each other out, correct? That's because we are of the same electronegativity, and based on that bond angle, we're having that occurs. Do we get it? Okay. Now, what happens if, Sharpay, what happens if Annalie becomes, you got to watch, more electronegative than me? See what happened there? Do you see how that's polar? Okay, so this is the thing. On that table, we're making the assumption that everything attached to the central atom is the same. But the second it becomes different, if anything attached to the central atom becomes different, it's going to make the molecule polar, just like what happened here. We were the same at first, but then she got a lot more electronegative. She made the molecule polar. Okay? So that's one thing you got to understand about that table. Now, lone pairs. For the most part, there's two exceptions to this. Great Dane. For the most part, and there's going to be two exceptions, if you have a lone pair in the central atom, it creates an asymmetrical distribution of charge. So to show you this, put your arms out. Now, he's going to have a lone pair on his back. So he's actually going to be a Trigonal Planar family, electronically, right? So just watch what happens when we lean forward. You can try all day, but you see how there is an uneven distribution of force, right? Same thing with the charge. So if you had vectors, they wouldn't cancel each other out. So if you can, however you want to think about it, that created a polar situation. So in most cases, if there's electrons on the central atom, pairs, they're polar. Okay, y'all can sit down and catch up. All right. So to revisit, I'm going to go to the chart now. And I'm sorry, those at home, you don't have this filled in. Our students have been filling them in as they have been listening to this lecture. Polar molecules, an uneven or how do you spell asymmetrical? Is there two S? Is it asymmetrical or just asymmetrical? Two M's and one S. Asymmetrical distribution, an uneven or asymmetrical distribution of charge or of electrons, okay? That is crucial. So, as we go down this table, and again, sorry at home, this is not filled in for you, but you can go fill it in, or go talk to your teacher, or go look in your textbook, lots of options. Molecular polarity. If we are that linear, and we have the same thing attached, two areas, no lone pairs, what is it? Nonpolar. The molecule. There's a difference between molecular polarity and bond polarity, and we talked about that, right? We can have we can have polar bonds and a nonpolar molecule, right? Okay. Three areas. Think about the trigonal planar. Think about the little guy in the center being pulled by three different things of equal strength. What is that? Nonpolar. Now the next one, if we have three areas, two bonds, one lone pair, that's what we just saw with JD. He had two bonds, one lone pair in his back. What happened? It was polar. Okay. Four areas, no lone pairs, tetrahedral, pretty even distribution, yeah? Nonpolar. Again, students get tricked all the time. I have students where if I throw CH3Cl at them, they're like, la 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 la. I'm doing the Lewis dot. I'm so happy because this is easy. It's tetrahedral. Oh, it's nonpolar because tetrahedral 0 is nonpolar. Zero lone pairs, all bonds, nonpolar. Why is that not true? We've got something different attached to the central atom. This is more electronegative. That creates a dipole moment. Okay? So what we're doing here down this table is assuming everything attached is the same. All right, 4, 3, and 1 we decided was polar, right? That was JD. No, that wasn't JD. This was JD. Here, this is trigonal pyramidal. Okay, that's polar. And then what about bent? Polar. And then we're up to our family of 5, Trigonal Bi-Pyramidal, right? What do we do? What do we say? Nonpolar. Whoa, that's like an entire pound of puppies. Like the 8 Austin Pets Alive just got bombed. All right, 5 areas, 4 bonds, 1 lone pair. That's seesaw. What is that? Polar. 5 areas, 3 bonds, 2 lone pairs. T-shaped. What is that? Polar. Now here you've got some asterisks. Here's an exception, and I can show it to you. Remember this poor little guy, these poor bonds? on this linear here are being repelled evenly from all directions. So even though there's lone pairs, there is a super even distribution of electrons. All right, so this is one of the two exceptions where having a lone pair doesn't mean you're polar. This is actually nonpolar. And the key is, remember, that goes back to 90 degrees. I mean 180, might be, 180. Okay, I hate that when I'm about to say something really profound and then I mess it up. It happens. All right, octahedral, nonpolar, square pyramidal, polar, and here we are again, our other exception. We have even distribution. Lone pair on top, lone pair on bottom, repelling up, repelling down, all nice, spread out nice and even, making this nonpolar. Okay? So what I want to do now, I'm going to, and you guys can go back in your notes, I'm going to pull up the filled-in notes from the day we did Lewis structures so we can practice applying these pieces of information. So now it's just a matter of me finding. This is weird. So it starts on this page. I'm going to zoom in. So weird. I've got to stay within the... Okay, I think that's big enough for the video. All right, so we're going to go through these, and you're just going to tell me, and I can't write on this, people at home, sorry. Well, maybe I can. Sometimes it lets me, sometimes, No, it's not a smart notebook, so I'm just going to have to talk. All right, F to S. What is the the electronic structure? Linear. There's no central atom there, I know that, but what's the distance between 2 points? It's a line, right? Linear. So it's electronically linear. Polar or nonpolar? Nonpolar, correct. All right, now I guess I'll use my cursor. All right, now let's go up here to ammonia. How many areas, first off? 4 areas, so it is a family that is tetrahedral. The family's tetrahedral, and then the geometric structure is trigonal pyramidal. And what's my bond angle? Bond angle. Less than 109.5, and is polar or nonpolar? Polar. It's got a lone pair, and it's not one of the exceptions. Okay. Any of these carbon dioxides, how many areas? 2 areas in all of them. So that makes them family and geometrically linear. Bond angle, 180, and then polar or nonpolar? Good, nonpolar. All right, CCl4, family, tetrahedral. Molecular geometry, tetrahedral. Bond angle, 109.5. Polar or nonpolar? Nonpolar. All right, this is the same. Let's look at one of these nitrites. They're all the same. How many areas? 3. So what's the family? Trigonal planar. What's the geometric shape? Trigonal planar. What's the bond angle? 120. And polar or nonpolar? Nonpolar. All right. BF3 is the same as that we just did. How about PCl5? 5 areas. Trigonal Bi-Pyramidal. They're all bonded, so the shape is Trigonal Bi-Pyramidal. What is the bond angle or angles? 90 and 120. And then polar or nonpolar? Nonpolar. All right, xenon tetrafluoride. Nope. 1, 2, 3, 4, 5, 6. So it's family of octahedral. Remember, it loses one, it's square pyramidal. It loses the other on the opposite side, it's square planar. So this is square planar. What are our bond angles back to? 90. And what's the polarity? Nonpolar. Last one, this guy. That is a trigonal bipyramidal, 1, 2, 3, 4, 5. It's linear, right? So let's go through that. Trigonal bipyramidal, if I were to lose one, it became that seesaw. Lose another, it's T-shaped. lose this one, it becomes linear. Is this, what's the bond angle? 180. Polar or nonpolar? Nonpolar. This is one of the two exceptions. Did we say nonpolar to this one? Okay, I didn't remember if we did it. All right, so that's the lesson. You have homework due tomorrow. I will not be here tomorrow. I shouldn't say that on video. I may be here if you're watching this in any other year other than 2016. Bye, people at home.